Hello.
Good morning. How are you guys?
All right. How are you?
I'm pretty well.
Good. So, welcome to another week. Another week finished. We had some good discussions in our meetings this week. For DevoWorm, we have Google Summer of Code going on, and we also have Google Summer of Code in the Orthogonal Lab open source meeting, which we talked about yesterday. We did a number of things, updates. We did some GitHub, sort of getting people, organized on GitHub, and then, planning for the home stretch of the projects. So, and then our Wednesday meeting, we had some good conversations there. We talked about a paper and a lot of research planning. So yeah, we've had some interesting things happen over this course of this week. Anything Jesse or Amanda would like to add?
My updates for this week are we had a nice Cognition Futures meeting. I actually really liked that meeting. We finished off. I'll say more about it later too if we have time for their updates. But we finished off the Stephen Richards and his take on like phenomenology and sort of what to do about it. And we went on to the next paper, which was by Lee. I think that Lee was the one about mechanism. I'm really looking forward to that one more too. A major theme for Cognition Future stuff right now is dealing with the analogy. It's funny because I kind of thought that submission to the Enies Hippolito Society for Philosophy of Mind conference, that paper about analogies for like brain to mind, or mind as a brain as a whatever, analogies for what the mind and brain are to these other objects or things. That was kind of a, hey, well, I don't know, I guess I'll put this together. And now it's like become a huge nexus point, landmark for a lot of my feelings about things. And I really want to make that paper happen, or at least flesh that out as like a thing. But the backdrop to a lot of stuff on my mind lately has been, along those lines of sort of what's sort of the mechanism in both the actual computational sense, and how are we talking about computation, which I feel like are different things often. Or how are we talking about like what's happening, and what how are we talking about specificity? And there's been a lot of stuff about I'll really briefly share my screen just to kind of show what I'm talking about, because it's something I think is fairly cool. Which take that for what you want it to be.
Well, aside from the mountains, yeah.
Can you see my screen though?
Yeah, looks good.
Okay. This is I really like this too. I guess I should say this is kind of a general review comment. But this actually left me smiling a lot this week. Also a little bit not sad, but very happy about Princeton Vision, which I'll say there. But I made this comment from after last week's meeting, and a week ago from this meeting where we talked about. I kind of did a summary, like, oh, we're talking a lot about these topics, a similar project, having space for interest to do X, Y, Z. And then Amanda shared this, which, very zoomed in, which was sort of commentary from the Macy conference series. Also, in the back of my mind, I kind of want to make like a T-shirt, like a retrospective. Like a T-shirt you get at a conference, but for the Macy's conferences. Yeah. And I'm thinking about how to do that. So if you're interested, you can you can let me know. I'll probably make it just a simple version. We're not going to do like a full, like I designed the labs t-shirt, and by the way, I have not made another batch of them yet, but I will. So if people want a lab t-shirt, send me your size and I'll see what we can do about that. I know Bradley, you're definitely going to get one whenever I make it next
Yeah,
batch.
yeah.
But I want to make it for the Mason Commerce too. But that's want is much lower priority.
Right.
Those mentioning digital, analog, information, probability versus improbability, symbolic and not, nature versus artifact. It's just a really cool quote. Sometimes though that happened, and I guess this is sort of this is basically my update still. But I've been thinking about Princeton Vision because I'm going through some like like old belongings and actual conference shirts and stuff, and um, how thankful I was for that moment of just having a bunch of people talking about stuff in the same room in the same way, um, and putting a lot of things from technology society and different fields of study on the table. There'll be more about that later, but excuse me, oh boy. What I wanted to say is I kind of went over this. It was really interesting to go through the mine is the paper, yes, but then also this tools for theory, which is from a Max Planck Center, CBS, I think Cognitive Brain Science or something like that. But Iris van Rouge, van Roij, went to this. It was about tools for theory for making like theories in like psychology, basically. And I've been thinking quite a bit about that this whole week in terms of the view of computation and the role of this is kind of the most, I know, as boring as it is, it's kind of the most, the picture I take away most from is this one, because he's basically saying there's the replication crisis is what it is, but and psychology wants to have these these scientific bricks, these scientific facts that are the bricks supposedly, and differentiating its psychology from like pure philosophy or maybe the kind of weird non-empirical things that have informed it in the past. And psychology wants to be rigorous in its own way. And she was saying like, yeah, that's great to do that, but the reason why there's cracks in the walls more because of the foundations and the bricks themselves. And it's kind of this sense of like, well, here's how we can make the best bricks we can make. But she alludes to, and maybe this is me spinning a bit too much. I can't really tell you. I don't know what speaker really thinks about all this stuff. I haven't done my due diligence to look at their background views about stuff. But what I'm taking away from it is basically we got to make the best bricks we can make, and there's computational tools that can help with that out. It's kind of interesting because this diagram to me is like, okay, from cognitive science, let's bridge through cognitive psychology and do this stuff in psychology, and we're kind of saying, well, did the cognitive science project actually work, and has cognitive science basically just become cognitive psychology anyway? So it's kind of like it's different sides of the coin, and you can kind of have some sympathy for why did cognitive psychology take over the way that it has. Why is in the Nunez paper, why did it become that way? Well, this is probably part of why, because it afforded the means for the psychology problem to have some computational founding, even if these other parts aren't the most ingrained in it. And there's a huge part of my mind in the background work is sort of how are we dealing with a lot of these big discipline / model / theoretical frameworks that what's the degree that can be integrated in cognitive science anyway? But suffice to say, I appreciate this picture and this discussion because for me, it was essentially an allusion to you can make the best bricks you can make, but you have to do them on the right foundations. Otherwise, they will have limitations. And that's come up quite a bit too. I don't know if that's part of what was in this quote here, but that thing about what are the foundations and what are the theories that are when you test them rigorously, they're going to hold or not. And what's the limitation? What is that? I don't know how to call it, but when we're talking about neurodiversity, and there's sort of this repeated stuff about on the margin versus what is like main domain for the theory and how things should be, or what is normal versus what is actually also part of the theory but more marginal and not as nuanced or articulately discussed. I feel like that's a major battle point for all this. So all that's been on my mind. We had a really good time with the Stevens book on his take on consciousness awareness, and we're reading an activism meets mechanism, which I think will be really great in light of everything we're talking about here, even just to kind of flesh that out. Also, next time we're gonna do the lead paper, the Raja paper, and this one looked though the Shear and Varela one too. But also, where's the one that was like all the different kinds of inactivism that was here? Anyway, I'll put that one someplace.
Oh yeah,
But
that was a different one.
That's my brief. That wasn't very brief, but that's my kind of where have I been this week? That's where I've been. Outside of the mountains, I've been on the mountains of exploring the different paper pyramids and everything else in that kind of journey space. That's my recap, I guess.
Well, that's good.
Oh, a little bit with Google Summer Code too, but I think we'll talk about that later. Do you know if Roger, whoever's going to be here?
I'm not sure, but I saw that he had met with Himanshu, who was a TSOC student last year, and they got together because Raj said in the meeting that he wanted to sort of do some work on the reinforcement learning stuff that Himanshu did last year, and so they got together and had a meeting about it, which is always good that you have that continuity of institutional.
Oh yeah,
thought.
that's huge.
Yeah.
Actually, that's something that I wanted to. Maybe I can have a soapbox sermon about it next time, but like,
Okay.
not just documentation, but like actually kind of intending to carry over your institutional knowledge. That's sort of like, especially we're looking about open source sustainability, like actually having some intention about that. And how do you do that? And like, we have ideas and strategies, but like making it a little bit more accessible, I think that's a huge thing. But yeah, I'm really glad that Raj is doing that, and I'm excited that Ankit's. It's always good to see Ankit. It's good to see him in a lab and see him be excited, and he'll put his ideas out there. And it's always great to see that. So with Ankit and Raj and Himanshu kind of having dialogue still, that's a special thing, and I'm trying to incorporate that. I don't know how to best say that, but like I want to put that on the Google Summer Code website eventually too, which is it's almost ready to be fully there. Like it's pretty much there. So yeah, it's good.
That's great. Yeah. And so Amanda, how are you?
Yeah, I'm good. I don't think I have any updates that weren't already mentioned or won't be mentioned later. This coming week we'll meet for the Weiner reading group.
Okay.
I would have to check to see what chapter we're on, but I know we left off with the question of how accurate exactly is his discussion of like Newton and the relationship between like scientific explanation and mechanistic explanation. So yeah, there's an open question from last time that we'll get to the next meeting.
A lot of good stuff.
It was also in the Slack. Let me see. Jesse says, I would like to further investigate Norbert's claim that mechanism was less important than mechanistic understanding until after Newton. And then another book I'm reading talks a little bit about Newtonian explanation versus other types of explanation. So we should we'll have a good discussion next time.
Yeah.
We left off with things we still wanted to talk about. So so I'm looking forward to that. Yeah, otherwise I don't think I have any updates.
Did we pick up from page 70 last time? I think so. Or did we end? No, we ended at page 70. Okay, this is it, right? Ah, okay. There's such anticipation for everything that yeah, we left off on page 70. We have not yet met since then. This is the one that's next, like later this week. So yeah, page 70. These are all things that this is a precursor to the physical computation stuff, which Riley had a great discussion on last week. If you didn't see it, go back and look at it if I need to. But yeah, I'm very curious about that question too, about mechanism or not. But yeah, thanks Amanda for you're doing this is a really great thing. And I'm looking forward to that. And also I'm thinking a little bit about I'm gonna write that down for myself. Like I've been talking all these things about discussion series and other things to read and whatever. And I want to think more about that. Maybe we can talk about that later today. But yeah. Great. Thank you, Amanda.
Yeah.
Thank you. Yeah, those are good discussion groups. I think we're making some headway, at least conceptually, on a lot of these things, and then we'll be working on these papers or at least the abstracts that were submitted to the conference that we talked about. And now I guess the goal is to flesh out the papers. So, that's something that catches up on you. So just to let you know, I mean, one moment you're submitting it, the next moment they want the paper. So it's good to always kind of do that gradually, and get it to the point where you can refine it, and you don't want to leave it to the last minute and just run through like writing everything out. And I just found that it works better if you kind of do that gradually. But we're continually working on refining the ideas, so that's at least good.
I would even say every meeting, anytime. I always appreciate people reminding me of that because I need help with that regulation a lot. So yes, one brush stroke, slowly, iteratively, is my goal for that. The good news of that, I didn't say frontier map explicitly, but it's frontier map is coming along slowly, but there is some momentum, and sometimes momentum is more important than progress, as our lab hidden motto might read. So yes.
All right, so that's all I think for updates. I wanted to highlight some of the things that have been going on in DevoWorm recently. So the last 2 weeks we've had a discussion on different types of embryo model. So I think 2 weeks ago we talked about human embryos and what they call embryoids. So you have these organoids, which we've talked about in this meeting before, which are three-dimensional cell cultures of different types of cells that differentiate into different types of tissues. So you have a bunch of stem cells that differentiate, say, into muscle and into maybe some precursor brain cells and some other tissues that just kind of organize, and sometimes you get germ layers. sometimes you get, groups of cells. They're not like, all mixed together in a mosaic. They're separated out by sort of tissue, almost like tissue layers, or like the 3 germ layers that we expect in an embryo. In the new work that's come out recently, you have these embryoids that are actually highly structured, at least for their stage of development. And so that's exciting work. We went over that. There are a couple papers out on that. Then last week we talked about the same set of experiments or certain different types of embryoids being done in monkeys, in non-human primates. So that's a nice comparison, across model organisms. And if you can do that in 2 different organisms, then you really have something. Usually that's the way it works. So again, these come from stem cells. I think actually some of the monkey work comes from induced pluripotent cells, which are, of course, where you take a somatic cell, a cell of a certain fate, a certain type of cell, like a skin cell, turn it into a stem cell, and then you turn it back into something differentiated from that. So that's where their embryoids are coming from. So we've had some good discussions on that, and that's Morgan has been providing some papers and commentary on that in the brain organoid channel in our Slack. So we have some of those papers in the Slack. We also talked about the physics of embryos. So last week we had a discussion on what they call shear jamming, which is where you have this phenomenon called a jamming phase transition in what they call the area of soft materials. So embryos and collective cell populations form what we call soft materials. So they're materials, but they have properties that are sort of emergent. They have different types of properties from harder materials. You're usually formed of little grains or little pieces that act collectively. So usually you can, they have different sort of collective behaviors that they exhibit, and so that's the way people characterize a lot of embryos, a lot of emerging tissues and things like that. So they use a lot of tools from physics. One of them is the idea of a phase transition or a first order phase transition, which is where you have these changes in state, changes in phase actually. And so one of the things we talked about is this jamming phase transition, where you go from a flow, which is a free-flowing medium, where you have a bunch of grains of particles, or in this case cells, moving, say, through a pipe. And they move at a certain rate, at a velocity, and then as they increase their density in that pipe, it's like a fluid usually, they start to slow down, and then at a critical density they jam solid. So you get these jamming phase transitions, going from a smooth flow to a solid. And this happens pretty quickly, so you can measure like a critical jamming parameter, which is usually the density of particles in this space, in this flow, and then when it gets to a certain density, it jams. And you see this in cell migration in embryos. You have these jamming phase transitions that occur where you get this migration of cells, this collective migration throughout the embryo, and then there are these jamming phase transitions where they get jammed together and they stop moving. And then you get these unjamming phase transitions or reversible phase transitions where things open up again and start to migrate. So we talked about the physics of that and the characterizing that. And then they have this phenomenon called shear jamming, and this is the review that we talked about in the meeting, where you can induce jamming through shear, and you can also induce unjamming through shear. And there are a lot of physical properties in the embryo that you can look at through this lens of soft matter physics. So we Susan is one of the other people in the DevoWorm group who's really interested in this. She's doing her dissertation on it, so it's of great interest to her. So we've So we'll probably talk more. We've talked about that a lot in the meetings this year.
Is she doing specifically that part of the embryo work you mentioned? Is
Yeah,
that why?
she's interested in like modeling embryos, modeling embryogenesis using a lot of the physical principles. So she's interested in the tensegrity work that we've been talking about this year as well. So that's where you have these super stable structures that form from dynamic tension. So that's it's another thing that we haven't talked about that in the last couple of weeks, but that's another theme this year that we've covered in those meetings. So we've got a lot of interesting stuff going on there in that group. And if you're interested, you can join us on Mondays at 10 a.m. Eastern. And we usually have our link on the DevoWorm website for that weekly space, or for that Jitsi space. It's yeah. Go ahead.
There's a separate DevoWorm Slack too, where a lot of the action is, and well, even more so on like GitHub. But yeah, I was gonna say something else. The meetings are also recorded. They're really good. I've only been partially in the last two, but I want to go back and look at them because it's a lot of the really interesting stuff that you've been talking about the last couple of weeks. So I recommend it.
Yeah. Then those meetings, of course, are also recorded, and we have a YouTube channel, DevoWorm YouTube channel, that is where all the meetings are. Those discussions are all posted and organized that way. So yeah, that's something that people might want to check out. Let's see. So yeah, the other thing I wanted to mention is that we're coming up very fast on Neuromatch, and Neuromatch starts I think the 10th of this month. So we're in a new month today, and on the 10th we're going to start Neuromatch. I think it's a Monday, right? Yeah. So that's going to be. We're planning on doing some things for that in the Saturday meetings. I'm going to be a faculty advisor for, I think, computational neuroscience. And I don't know who's taking the course, but we do have this sort of, we talked about doing a slow pod. We might end up doing something like a deep dive pod where we pick a topic, or I'll pick a topic, and we'll talk about it. Last summer we did a sort of a fire hose pod where we went over everything for that week, and it was just kind of like we maybe picked one thing. But yeah, I would like to at least have like a discussion every week on one of the topics from that week or that theme. And you don't have to attend the class, or you don't have to attend the summer school to get something out of it, because there are topics that are quite relevant. Maybe tailoring it more to what we talk about in the meetings, which I think is better because, as we've mentioned, they teach a lot of things that are very specific to in the computational neuroscience course, very specific to computational neuroscience. So you have these some of these models that we've talked about in the context of active inference. We have models that, like Bayesian models, which are useful generally, but not necessarily anything we're currently doing. So there is that we can like make this relevant to our group and what we're doing. So that's what I'd like to do. Yeah, so that's going to be coming up. But it looks like Jesse has and this is what I wanted to get to next, was the submissions and the calendar.
I actually thought, for whatever reason, I had it in here and thought in my mind it started the 17th, but it is 3 weeks.
Yeah.
Well, I mean the 10th through the 28th anyway. So I just adjusted this to show that it's 3 weeks long. I think we should.
Even the fire hose review last year I appreciated. So yeah, whatever form we want to go over this in. Yeah, I got a lot out of it last summer. Just being exposed to to what, I guess I didn't really know what Neuromatch was before that. But being exposed to like the curriculum was, I like just appreciated the context, because although it was a lot and a lot of it was very tailored, I mean, even some of the more tailored stuff was relevant to, I guess I didn't have the job I have now at the time, but it is relevant to my research job now. So yeah, whatever form we want to go over that in, I'm looking forward to it.
Yeah. Thanks for giving some feedback on that. Yeah, I know we did have a good time last summer with going through some of these concepts, and I think they have the entire sort of curriculum online. They have the videos, they have some of the materials to work out, like data analyses. So this is definitely, if you're interested in sort of getting some neuroscience skill or some computational neuroscience skills, this is always something to dive into more deeply. So they do have the all the like they have digital notebooks and things like that available for people.
We have a curriculum for them too, don't we, somewhere online? I know we talked about that many times. There's actually part of the education banner that I'm supposed to, webpage banner that I'm supposed to put together eventually.
Yeah, I mean, it's I think so. Yeah, I think that's where we're getting like a lot of and I think it's right off the website. And I don't know how they've changed it this year, but last year was. I think deep learning will change more given the ever presence of large language models. But and I'm actually interested to see how they do that. By the way, which is, how do they talk about those kind of models relative to what they've talked about in years past. Because years past, they haven't really put that much of an emphasis on large language models, but this year you can't really ignore it. The hype has been everywhere. So, yeah, but I mean, like they do provide these notebooks and things like that. So there's a practice aspect. The students will be doing projects, which is what the faculty mentor does. They just basically advise on the projects and help people. So that's something that might be depending on the project. I might bring some of that more generally, and then hopefully I don't know. It should lead to some interesting directions, because I think a lot of times what happens in our meetings is that we have something that we talk about and then it gets fresh in our minds, and then we use it to our advantage. So like what we do with New York Celebration of Women in Computing, we often have a set of discussions, at least around ethics, and that kind of brings maybe some projects to the fore where, as before, we wouldn't have been focusing on them. But I think definitely we should get ready, dig out the curriculum, see maybe what we want to do. If Amanda or Jesse have a specific topic they really want to talk about, I think that's worth kind of saying, oh yeah, we should do this. And so, just to make it maximally useful.
We should make
Bradley, you said you're doing the computational neuroscience track?
Yeah. Yes.
Okay.
I guess we'll do this too. But yeah, I mean, do we have any? We can say this more next week, I suppose. But do we have anything? I know we just said a bunch of stuff. Is there anything we want to say for a discussion series? We basically mean kind of every week going forward having a segment where we talk about stuff related to Neuromatch, basically now to the end of the month? Is that kind of what you're imagining? Or
Yeah, I mean, like probably one deep dive a week into something.
okay,
But like we also can talk about specific, like more general things, like a overview of the curriculum. If we've like if things have changed from last year, or maybe there's something we don't really want to do a deep dive on, but we want to know more about, like what's a POMDP model, for example. That was relevant to Brian's GSOC project last year, and I know you picked it up at Neuromatch because that's what they talk about Neuromatch. So they also talk about an active inference. What was that? POMDP.
Oops,
Yeah.
I didn't hear that. P what?
POMDP.
Okay, I didn't have it right. Okay, sorry.
Yeah. Or you have V instead of D. But yeah.
There we go. There we go.
I mean, it's just an example I've given. Yeah,
But yeah, I think going through that stuff would be having a segment will be good. If I'm still leaning towards doing the deep learning one. So if I do that and we go to that, maybe I can talk about one of those topics.
oh yeah, definitely. Yeah.
But I don't know if there's anything we like. I don't know if Amanda wants to talk about something. I'm doing this like nudge for if people want to say, oh, I'd like to talk about this. You know, we can put it down on the list.
I'd like to talk about anything related to network science that comes up.
Like network science in general, network neuros.
I'm looking at the schedule now, and it looks like the last class is network causality and graduation. I don't know what graduate. Oh, probably from the class. But yeah, so network causality. I'd be interested in dynamic systems theory stuff.
All that Conrad Cording causality work. He needs to have just 3 Ks and one the case be for causality, like Mortal Kombat. I should offer that to him somewhere. Make a meme about it. No, what if we unofficially run a Neuromatch meme contest inspired by Ines Hippolyta? That would be pretty.
Causality courting, yes.
Anyway, if we host it, this is nefarious. Jesse says, if we host it, then I can control that my great courting causality idea would win, and that would be one way to the causal outcomes of things. So let's move on to anything else for Neuromatch. I think that's great. That'll give us some things to kind of. Here's your little presentation time about that, and that'll be good for us to do because we always have to stay sharp on our ideas, generation skills. Oof, I keep thinking about the expert writing stuff too. I want to. Okay. I want to do a lot of things with that through Joe Pro and through what we're doing here too. I think expert writing is an amazing concept for what we're doing and relevant to a lot of the theory work we want to do. But anyway, anything else for Neuromatch?
Nothing for now. I think that'll require a little bit of work on my part and maybe some of our other, some of our parts. But yeah, I think that'll just be like, going through and having a weekly check-in on that and having our features. I think like main things here, Vika is being in the process of being submitted, so that final version is being submitted. The conference is in September, I believe, or October. So that's that. Then the next step in that is going to be like a presentation on that topic. So Vika is the biologically inspired cognitive architectures conference, and they always have a really nice mix of people there, sort of doing. I wouldn't say, well, no, they do AI. You get people who do all sorts of different types of artificial intelligence, cognitive architectures. So there are a host of questions and issues that come up there. This is it's being held in China, but also online. So it's a hybrid conference. It's in October. So the camera ready papers due soon. That's almost done. Then there's a presentation that will be due by the conference date.
Which paper? This is just the one that you did, right?
Yeah, this is the Super Performers paper.
Okay, Super Performers.
And when I get that talk done, I'll put it on YouTube and we can talk more about it. I got some nice comments from Ankit on that actually, and he was making the connection between that and like a lot of the questions in deep learning and machine learning, mainly with respect to data, the need for data and models. So there's this issue of training models, exposing them to data versus not exposing them to as much. How much data do you need to train a model, basically?
Mm-hmm.
And so there's a nice. I added in a nice discussion about that, and I'm going to acknowledge them. So there are going to be two versions of this. One is in the conference paper, which is very abbreviated, and then there's going to be a longer preprint on archive that will have everything in it. So that's just by design because you don't have room for everything. You don't have room for very much in the conference paper. It's really chopped down. But that's what we did with the Gibsonian information work as well. We do have the conference paper and then the larger preprint. So, speaking of the Gibsonian information paper, well, let me have you catch up here. Speaking of the Gibsonian information paper, I think this has kind of been put aside for a while. It's been over a year where we've had these discussions about it, and
is that on here or should that be on this list? I don't remember.
Well, yeah, that's an interesting thing. We could make it as a free floating item because we have a preprint that needs to be updated, but we haven't put out the update yet. This is like we had the conference paper at BICA in 2022, I believe, and then now we're going to have this updated preprint, which is
I don't think Gary Marcus is
on it. Yeah, but that's and then that's going to have some more detail about some of the methods and things. So that should be good. The preprint has a slightly different name than the conference paper, but I really want to kind of have a larger reference where we have everything kind of put out in a form where you can follow along. Just because these conference papers are very abbreviated. So when that's done, we can talk more about what to do with that if we want to publish it.
The Gibsonian paper?
Yeah, okay. The bigger one. So
is this the right one or is this the other one? This is the agent-based one. So
I can't remember which one is which.
There's like kind of a few versions of it out there, right? Like.
Well, the conference paper has one subtitle and the preprint has another subtitle, and I can't remember which one is which right now. But the point is that the preprint, which might be the agent-based, I'm not sure, is the one that is going to be updated, and then maybe we could make that into a journal paper or something. But we'll see. But this is this sort of strategy of like moving along. You put something at a conference, you get a conference proceeding, then maybe you move on and you give more detail on another paper, and you do more conference presentations and things like that. So you just move along these topics, and sometimes you don't want to self-plagiarize. You don't want to copy stuff and move it in. All right, so I tried to sort that out so that we don't have that problem of self-plagiarizing. So that's kind of a model for like moving projects forward and having, going from like presentations to small papers and large papers to other conference presentations and so forth. So with that being said, I mean, this conference, you have up the first annual web conference of the whatever it's called.
See, we're going to be notified about this. There's not a lot of dates. It just says you got to submit your stuff by the deadline. There's no we're going to let you know by whatever date's listed on it. So okay.
Oh, I thought I remember reading July 30th.
Oh, really? Okay, that sounds good to me.
Because the conference isn't until November, I think.
Let's check. Let's update this to July 30th. Yeah, the conference is it's one of those like 6+ months. It's five months difference, which are always those are the ones that get me. Because that's like, yeah, you can do the whole paper in that time, and some things you have to have ready to go because of the quick turnaround, and then something you can build your efforts across.
Yeah, so for this, I would recommend, like, if you, I assume you might get in, but if you don't, having something there, you can put it somewhere else too. Or
right,
if you
that's
get accepted,
still a paper I want to put together.
Yeah.
Oh yeah. Maybe we can spend a little bit of the next meeting, like I don't know, like part of the project management time on just talking about those papers and saying what's our next step for both of them, or just I don't know, just to put it on our progress watch for that. I'm gonna make a note of that before I forget, because I'm totally gonna forget that I said that.
Yeah, and I think, like, kind of thinking about it in terms of not just the paper, but the presentation, and then if you have like other papers that were like other types of ways to present it, have those kind of in the back of your mind, or like make notes about, like, because you're going to have, when you write the paper, you're going to have sections of the paper, and you might have to cut parts of it, or I don't know what the limitation. I don't think there are limitations in this conference, but sometimes in conferences they require a shorter version of what you want to say, and so that's a problem. But sometimes not. But sometimes there's so much in a paper that gets kind of forgotten about. So, like some of our papers, we write a paper, and it's either really dense. I mean, papers tend to be dense, or people forget about things. And so I want to kind of make a New Year's resolution here to say, like, we're going to try to pull stuff from our papers and kind of bring it out into the world. So, like, we just have a lot of stuff gets like put into papers. You write the outline, you put the detail in, and there's a lot there that can be followed up on, but also a lot there that can just be, there's an exposition part. So what do you mean by this concept? Or what do you mean by this idea?
Mm-hmm.
We kind of done that with some of the conference talks, but like we tend to work from a general to specific. So it's like a very general idea to specific ideas. The specific ideas could be like, made, brought alive, which is, I think, a good idea, because I think there's a lot of stuff in papers that gets kind of put in there and then forgotten about. And then you're like, oh,
and
yeah.
then, I've been thinking about that too, is like building upon it. Like I've been reviewing the part of what I put in I think one of the comments in the just is like reviewing the interface focus paper, because there's stuff I feel like I've like blanked on some of the developments there, but you mentioned tensegrity, you mentioned these other things, and like just like like pushing some of those concepts forward, even if it's like blog posts or whatever, but pushing those things forward and building out kind of, as we can tell by the Cognition Futures stuff and everything else, I think I'm significantly more aware of like the work to actually push some theory stuff forward. And I'm glad that you mentioned that too, because that fits. I haven't put it in that framework in my mind, but like, let's actually do that where we're putting where we really intentionally build out that stuff, because I think that's fun and difficult. It's hard, but it's also like, I think there's sort of there's a certain sort of craftsmanship to it, and even like the open source sustainability stuff, like it's not just writing the code, it's sort of maintaining the idea, like idea maintenance, which is weird. I think that's something
Yeah.
that, I don't know if you talked about it like that before, but I'm kind of seeing some parallels of that too. So I think there's so much there. There's so much in these papers from the last like 3 or 4 years since I've joined the lab that I've only like partially understood,
Yeah.
and they keep coming up, and I feel like making the papers sort of like things that we know and talk about and really build on would be great. And the concepts within them too.
Yeah. Well, that was
I would,
Oh, go ahead.
I would definitely be into digging more into the Gibsonian information stuff, because that's some of that's new to me. I'm sure I could find it if I tried, but could you share a link to the paper or papers?
Yeah, it's I don't know if Jesse. Well, I'll put him in the Slack.
Okay.
Yeah.
I'm gonna put a reminder in Slack right now to do that, because I know I'm gonna forget. But I'll see it here.
Thank you.
Yeah, I mean that's what happened with the interface focus paper. Actually, is that it was like we had a page or a word limit, and there were so many ideas that we could have fleshed out more,
Yeah,
but we didn't because we didn't have the space.
Mhm.
So that's the limit always that you run against. Like people don't always want like a 20,000 word paper, so it's definitely something that can be. You have other venues to do that sort of stretching, and that's why that's something I want to do. So yeah, and then that helps us with like submissions to other things like conferences. It's like a natural lead into that. Like, oh yeah, we have this thing that we stretched out from a paper on this, and we should do this as a standalone thing. You so yeah, I wanted to get actually into the discussion today that we talked about. So let me go back here. All right. Yeah, I'll just share my screen and then you can follow it. So last week we talked about, and we'll come back to this later maybe. We talked about physical computation, and one of the things that we've been talking about in Cognition Futures is about computation and phenomenology and like cognitive science, and how cognitive science is sort of computationalist by nature. And then if we talk about the computer as a brain, what does that mean? What does that imply? And so people have been talking about something called pan-computationalism, which we talked about last week, which is that you can apply computational models to any system in the world. It's just a structural sort of description of a thing. So you can have like a brain, you could have like a living system, like an immune system or circulatory system. Those things are sort of pan-computationalist in their nature. And you can model them with things like cellular automata and other types of computational models. They may even perform computations on their own. And there's this idea of, we talked about the Church-Turing-Deutsch thesis last time, which is a different way of thinking about computation from the traditional digital computer, which is, the computer or the brain might obviously not be like a Church-Turing type system, but it could be something else that's computational. So the Church-Turing-Deutsch thesis is sort of moving computation towards a more sort of physical formulation. So with that being said, I'm going to share my screen. And yeah, and so this time we're going to talk more about the sort of physics of information, because last time it turned out that we were talking about the physics of or physical computation. We're actually taking cues from Corey Maley and Gualtiero Piccinini, who are two philosophers who talk about computation and physical computation and linking those to the brain. So this is going to be a little bit more in depth about the sort of the physics of information, which is kind of like treating physics as a computational thing. So first thing I want to talk about, this is a paper from last time that I kind of glossed over. We talked about this abstract, when does a physical system compute? And so this is where, we have physical systems in the world, and they have physics. So this is something that, like we said, maybe natural systems like biological systems or physical systems don't behave like sort of a digital von Neumann computer, a digital computer, but maybe they still do compute. So, how do we describe that computational process? Maybe we need new descriptive tools for this. Maybe this isn't just, maybe the old Church-Turing thesis isn't going to cut it for this. So, so let me go over the abstract again so we can kind of get on the same page here. So they mentioned computing is a high-level process of a physical system. So the high-level process is not sort of at the fundamental level, it's higher up. And they're talking about computing as like they're just kind of computer scientists interested in the nature of computing. But they're also thinking about putting computing out into the world. So recent interest in non-standard computing systems, including quantum and biological computers, has brought this physical basis of computing to the forefront. So there are things called quantum computers, which are basically computers that have a bunch of measuring a bunch of electron spins in atoms and then calculating their calculating the probability of their quantum states and using that in lieu of like a bit flip that you would see in a digital von Neumann computer. So a digital von Neumann computer basically uses silicon, uses a logic gate, and you have a flow of electrons over that gate, and the logic gate controls the flow of electrons through a band gap, and there's this thing that's calculated. It's either a 0 or a 1. And one of the things that we've had a problem with in the era of von Neumann computers is that when you make the chip small enough, or when you make the circuit small enough, you end up with leakage across that gap, and so that can interfere with the binarization of the signal. So you can have a 0 or 1. The logic gate will either block the flow of electrons or enable it, and that's a 0 or 1. And then that 0 or 1 is used as a way to describe the state of the circuit. With quantum computers, it's different. You have the probability of quantum states. You calculate that across a bunch of atoms, and you can basically have a quantum computation. So that requires a shift in how we think about that computer as a thing and how computation is done. And so we have to rewrite our programs. We can actually implement very simple programs in a quantum computer. They're analogs to things we can implement in a von Neumann computer. But the process of getting an answer is very different. And so that's one example that you can use that actually shows this difference between, like, say, a physical system computing one way and a physical system computing another way. Then they bring up biological computers, which are, of course, we'll talk about some examples of those later. But there's some nice examples from fungi and other collective behaviors of organisms that actually do computation very differently than the von Neumann computer as well. But they do give answers to things. You can actually program them so that they have that sort of, they can give you a state. that's an output. So this is, there has been, however, no consensus on how to tell if a given physical system is acting as a computer or not, leading to confusion over novel computational devices and even claims that every physical event is a computation. So I think this is a key point. When we talk about quantum computers and when we talk about biological computers, we talk about the brain as a computer. We're kind of making an assumption that there's a computer or a computational act. That's not to say that there isn't computation, but if the brain does something to process information, or if there's a physical system that processes information, is that what we might call a computation? This is really kind of a hard problem because, you know, we can say, what is a computation? And you can give it any definition you want. And then, is that consistent for that system? Well, yeah, you're saying computation. Like, say, for example, I have a quantum computer, and I say quantum computing does computation this way. I can come up with a theorem to prove it and everything. Can I transfer that back to von Neumann computers, or can I find like a bridge between that and von Neumann computers and say, well, von Neumann computers do computation this way. My quantum computer does computation in an analogous way, and it's computation, I can prove it. And then my fungi that I'm observing, do they do computation? Or my little tiny brain that I'm looking at, maybe it's the brain of an annelid, which is actually quite small, but it does maybe it does computation. But I have to define what computation is in each of these contexts. I can't just use like the Church-Turing thesis and apply it all across these systems. But I also want something that's sort of universal, ideally universal. So I want to have something that I can apply not only in these different systems, but I want to have something I may be able to simulate, say like in a cellular automata. So that's why we're interested in this. And this is a question I think that's worth thinking about more, because we could say that a physical event is computation, but we can't necessarily prove it, or it doesn't look like another system that also does computation. So in this paper, we introduce a formal framework that can be used to determine whether a physical system is performing a computation. We demonstrate how the abstract computational level interacts with the physical device level. So, they're computer scientists, they're interested in sort of how computing, not only the definition, but how it's implemented in the wetware or the hardware or the physicsware or whatever. So this means that there's this computational stuff being done. There's this, state that gets output. There's an output of a state, a 0 or 1, or maybe a probability or something. It's being computed on a substrate, which in the case of a von Neumann computer is a silicon circuit, and you have logic gates that control the flow of electrons, and that gives you an output. Fungi, it's not going to be like that at all. It's going to be something else. There's something which we won't talk about today called DNA computers, which actually have, because DNA is, there's specific chemical structures that have for each base, for each nucleotide. They have, they can give you a discrete state. You can use that as a way to generate these discrete states over time and give answers that, are computational like. And so the question is, what is the substrate? What is the computational level that, or how is computing being done? So those are things that we have to think about. And then they compare that to mathematical models used in experimental science. This powerful formulation allows a precise description of experiments, technology, computation, and simulation, giving a central conclusion, which is this: physical computing is the use of a physical system to predict the outcome of an abstract evolution. So basically, physical computing is taking some physical system. It could be a quantum computer. It could be a biological computer of some type. It could be a von Neumann computer. And we can use that to predict the outcome of an abstract evolution. So that's what they're getting at, which is basically, it's very similar to the whole church Turing thesis and the idea of the tape and predicting or doing the halting problem with a physical system. So the halting problem, to recap, that's where you have a tape that goes through this head. The head's reading the tape, and you have to predict when the system will halt. And so that's what you're trying to do. But you're doing this in a different way because there's no tape. There isn't even like a head. You're just kind of like, when we do this in DNA, is to have, during transcription, when you have the strand of nucleotides or the strand of DNA that comes through the transcriptional machinery, and sometimes there are termination sites, and we can predict where those are, but sometimes it's like maybe that can be used in a DNA computer to sort of turn off a DNA computer, turn it on, or sometimes it might halt in some place where we don't expect it. So sometimes the kinetics of that process are different. So, there are ways that you can do this with computers that are not von Neumann computers. That, I guess, would be computing. But again, we'd have to have a discussion about that. So we give conditions for computing, illustrated using a range of non-standard computing scenarios. The framework also covers broader computing contexts where there is no obvious human-computer user. We introduce the notion of a computational entity and its critical role in defining when computing is taking place in physical systems. So they have this term computational entity. And so this is something, again, that is, again, we have to define what a computer is, but we also have to define what a computational entity is. So, we don't have a user like we do in a von Neumann computer. We have maybe an interface with a system of some type. What is it? What's the entity? So that's, I want to go over that. Oh, hello, Morgan. How are you? We have a couple things okay, that's just hi, Morgan. So that's the first paper, and I wanted to go over that just as like a baseline for what we're going to talk about. I kind of wanted to get into some of these other papers. So I talked about this book last time, and this is Feynman's Lectures on Computation. And this is something to be had in a bookstore or maybe online. There are different versions of this, but basically Richard Feynman, the physicist, gave a number of lectures on computation, and his estate has really kind of marketed his work quite aggressively, and they've put together his collections and books that are, pretty well known. This is Richard Feynman when he was younger doing work. And this is just a collection of his lectures on computation, where, he just gives lectures on things, and they've kind of come together. So it's not like a book he wrote that was well polished. But this is organized by talking about computers, the file clerk model, instruction sets, and summary. I think these lectures were done in like the late 60s, early 70s. So it's a little bit different than maybe some of the stuff that we would know today. But I think it's good to go back and look at like some of these lectures and think about the very fundamentals of what we're talking about when we talk about physical computation, the physics of computation. So this kind of goes through instruction sets, the file clerk model. This is an introduction to computers. Very, very basic, sort of what a computer does, Then there's computer organization. So we have our timing and shift registers. We have our flip-flops in computer memory. Flip-flops are just like kind of how states flip between zeros and ones. And then that's encoded in a computer memory that we can retrieve. The memory, by the way, has to be encoded in some sort of physical medium. So it's usually in either like a random access memory or read-only memory. Random access being the thing that's running. If you look at the history of cognitive psychology, they talk about working memory and long-term memory in that way. They talk about it as RAM and ROM. And that's an analogy that they use. It may or may not be exactly right, but that's the analogy they use. So interesting aside here, he's talking about the physics of this process, which, of course, there's a physics to like a standard von Neumann computer that you can also use to look at how you might encode computer memory in things that are not silicon. So there might be examples of things in biological systems and molecular biology that we can use as a memory, as a RAM and a ROM. Something we can access and actually do active computations on, and then maybe like a memory that's a read-only memory or something where we store computations. So DNA when under transcription versus when it's zipped up in its double helix and in the wound up in the nucleus is actually a good example of that. But I'm not going to make any more comments about how that might work. So then you have operators, which are logic gates and ways that you can transform different inputs into outputs. You have reversible gates, the binary decoder, gates, and combinatorial logic. So there's actually something to say about logic gates and about gates more generally, reversible and irreversible gates. So logic gates are these systems where you have a command that's usually something like and or exclusive or. And what happens is it takes a bunch of inputs and it uses that rule to sort of sort them into an output. So I may show this real quick. If we have an AND gate, and I'm just using a very simple example, we have an input 1 and an input 2, and we have this gate that's right here, this circle here. So these are inputs 1 and 2. Our output is here, this box. So an AND gate is basically a rule we implement here. And it says that you have to have both of these active in order to get a state. So both 1 and 2 have to be 1 in order for this state to be 1. Okay, so that's an AND gate. And then an OR gate would be like this, where you have the same structure, you have 1 and 2. Now in an OR gate, you have to have either 1 or 2. So if 1 is active and 2 is not, 1 is 1, 2 is a state of 0, this is 1. If 1 is a state of 0 and 2 is a state of 0, then this is a 0. If 2 is a state of 1 and 1 is a state of 0, this is a 0, or this is a 1, and so on. And so from that, you can build these truth tables or these logic tables that show the state. This is these are states, or these are inputs. These are our binary states. And then we can say, like, what is the state of, in an OR table, what is the state here? So we can, put our 0 or 1 in here. So if 1 is 0, 2 is 0, what is this output? We can draw these truth tables. I'm not sure I did this well. It's fine. It's just the point is that you have this contingency table that tells you the possibilities here. So, in an OR gate, you have, in an AND gate, you have a lot of flexibility. An exclusive OR, it's a little bit more restrictive as to what is a 1 and what is a 0. Basically, it's an activation function, as you might know it in neuroscience or computational neuroscience. So an activation function, again, is where you have these rules that sort of determine a threshold. And so this is computer organization. We'll talk a little bit about logic gates in a lot more detail, because as it turns out, when you get into like quantum computation, they have some really wild logic gates that people use. Really interesting types of structures that are much more like something you would find in like dendritic computing or something like that. So they talk about the theory of computation, and this is all stuff that we talk about with respect to physical computation, or we talked about a little bit last week. This is where I think a lot of this debate could be improved about the brain as being a computer or physical systems being computational. And then, ultimately the brain is a substrate for these computations. So what is the theory of computation that supports that thesis, hypothesis? What is it about the theory of computation that helps us understand that? So, we have these issues of computability, which is what things can be computed. There's a whole set of theorems around computability. There's finite state machines, which are these systems, and I've shown them in meetings past, where it's a bunch of binary states that are connected through these pathways. So you're activating things and you're moving from state to state. You send a signal that where the system transitions from one state to another, and you end up with these finite state machines that describe a system as a set of finite states and their transitions. You have Turing machines, which we talked about. You have universal Turing machines, which are like a more general view of Turing machines, and then computability again. So he talks a lot about the theory of computation, a lot about coding and information theory. So when we talk about zeros and ones, we have to get those zeros and ones from somewhere. So we kind of do a deep dive into information theory here, where we talk about information is data compression. There's a geometry that we have to worry about how messages are stored and parsed. And then, we have Shannon's theorem, which of course is calculating information from a set of binary states. We have different types of codes that we can be interested in. And codes are interesting because they're sort of a series of zeros and ones, and their properties to codes. So Shannon's theorem is basically like the diversity of a string of binary numbers. So if you have like a set of zeros and a set of ones, there isn't a lot of information in the sequence, because I could predict what the next state is from this. We have 5 zeros and 5 ones, so this next state must be a 0, and we're going to probably have 5 zeros and then 5 ones, and this will repeat. So you can actually make predictions. The same thing with this sequence here. Well, okay, I can do that. No, I'll do this. So this is just like alternating zeros and ones. So you can get information out of this. This has like low information. Something that's like this might have high information. This is higher information, I guess. All right, and then so on and so forth. Basically, this ensemble has to have a certain sort of information content, which is what we say when we talk about the parameter h. So that's their information content here. Now, codes are interesting because they actually compress these signals. So whatever information is in this sequence, it gets compressed into a code or into a set of digits that is that takes all that information and it compresses it down into a smaller representation. So we might have like a representation like this, which encapsulates all of this information just in a different form. So sometimes the codes are lossy, sometimes they're lossless. Lossy codes basically take out all the redundancy and give you a code that basically has the same information, but sometimes you lose a little bit of information in the process. And then lossless codes are things that are where the code is preserved, or the information is totally preserved, even with the noise and the redundancy, but it's just reduced to that code. So when he talks about codes and coding, that's what that means. And there are different ways that coding can proceed. So we have things like Huffman coding and other types of coding that happen in information theory that we can use to inform computation. And those things actually can also exist in physical computing as well as in von Neumann computing. It talks about reversible computation and the thermodynamics of computing. So this is something that we've talked about a little bit in Cognition Futures, and I've been meaning to do it. I have a talk actually on this, so I've been meaning to cut this in a video and kind of go over this for people. But he talks about like the thermodynamics of computing very specifically to some of the problems you might find in physics. So he talks about the physics of information, reversible computing, the thermodynamics of computing. So is there a reversibility of computation? And of course, reversibility is where, thermodynamics is this time-dependent process where things unfold, and then there's an entropy where it means that you can't rewind the tape, or you can't go in the opposite direction. You can't go back in time because the entropy you lose doesn't allow you to reconstruct going back in time. So time is a one-way arrow. And so this is where reversible computation comes into play. Because the question is, if computation is happening on a physical substrate, can computational operations be reversed? Can they be unwritten, or can they be rewritten? And there's in the videos on the stuff that I'm going to talk about in these videos, that's actually a big issue. We talked about demons in our meeting, and one of the things about Maxwell's demon is that there's this idea that reversible computation is impossible. It really requires some sort of something we can't describe. So if we have a reversible computation where we want to erase a bit that's been generated, we have to spend a certain amount of energy to do that. And so there's an entropy associated with that. In Maxwell's demon, the argument is that you can sort out different output states, different binary states, by using nothing more than random processes. And of course, what that represents when you go from, say, a random collection of balls to a sorted collection of balls, is that that's not a random process. That's something that is actually reversing that process of randomization. And it's requiring energy, but the question is there's a thermodynamic component to that. So then there's computation, energy cost versus speed. So the general reversible computer. So these things, again, have to do with entropy, thermodynamics, energy usage for computing. Then there's the billiard ball computer and quantum computation. So his take on quantum computation is pretty early days. There's been a lot of work on quantum computation since. So that area can be updated in the book. I don't know how he treats it. I haven't read this book in a while, but it's definitely, they're making some strides in quantum computation. So I would definitely follow the literature on that. The billiard ball computer is this problem that's common to physics, which is that if you play billiards, that you have say a cue ball, and you hit the cue ball, you shoot it, you hit it with a stick, and then you hit other balls. And so the object of the game, of course, is to hit another ball and put it in a pocket. But the idea of taking the cue ball and hitting another ball requires you to calculate trajectories, and then if that ball hits another ball, there are a bunch of trajectories that are generated that can be maybe calculated, maybe not. So it's kind of like this multi-causal system where one thing causes another thing causes another thing. And the idea is, if you can predict those trajectories, then you're in business. And that's where it kind of gets this idea of a billiard ball computer. It's a nice system where you can actually measure interactions across the system. So that's something that you won't find in the typical brain as a computer debate. So then he talks about quantum mechanical computers and some of these things about physical computation, like VLSI circuit construction and energy use and heat loss, and the physics of semiconductors. So these are things that talk about that substrate in terms of physics. So that's the Feynman lectures on computation. I would dive into those sometimes as a historical aside, sometimes as something maybe we can, take insight from more directly. So I talked about logic gates, and so we talked about AND gates and OR gates. They're not gates where a specific input is forbidden. If it's a 1, then then you get a 0. If that gate is not active, then you get a 1, more or less. That's how it works. The Toffoli gate is an example of a CC not gate. So this is a universal reversible logic gate. So this is an example of reversibility and irreversibility in logic gates. So CC not gate is a sort of a higher level gate that kind of gives you this. It gives you this sort of, I don't know if they use it. I guess they use it in quantum computing, but it gives you this little higher, different level than the classic gates. So so a universal reversible logic gate means that any classical reversible circuit can be constructed from Toffoli gates. So you can use a Toffoli gate, and the rule here is CC not, to reconstruct any classical reversible circuit. Basically, it's a description of this circuit and what it looks like. You can design this on hardware, you can simulate it with software, you can apply it to any system, at least in terms of the way that we think of computation. So if you have a substrate that has the components for computation, you can implement this. And it's like a sort of a computational model of computing, if you can think of it that way. It's also known as the controlled not gate, which describes its action. It has a 3-bit register of inputs and outputs. And if the first 2 bits are both set to 1, it invents a 3rd bit. Otherwise, all bits stay the same. So you have, in this case, it's CC not. If the first 2 bits are set to 1, it inverts the 3rd bit. So if you have, for example, let's go to our board again. We have our 1 and 2. Should have probably given them A and B, but whatever. We have our gate here, our CC not, and then we have our output. So if 1 and 2 are, we'll have our chart here. So if 1 and 2 are 0, then the output is 0. Well, actually, I guess that's true. If 1 and 2 are 1, we also have a 0. So our output is, I guess this is the way it works. If you have, so again, if you have this, if the first 2 bits are set to 1 and inverts the 3rd bit, otherwise all bits stay the same. So yeah, so you have 0 and 0, 0, 1 and 1 are 0. And I guess that means that 0 and 1 are 1 because you're passing through a 1. So you have this and then this here, which is 1 and 0 is 1, or something like that. Basically, if you have this state, it's inverting it. If the state is 1, if it's 0, then it's 0. It could be 1. I don't really know what the rules are. But the point is that it's this sort of inversion. So there's this very specific set of rules that is basically mapping these inputs to an output. So that's what we're doing here. And I'm kind of trying to get at the heart of what computation does. It's basically transforming something from one set of states into another. It's also taking multiple states and it's mapping it to something. So, we think about how we use neural networks. We have a bunch of states that get generated. We use a threshold to give an output. That threshold then is based on something. And so, we have weights, and then there's a threshold. And those are all based on something. So this sort of transformation is key, I think, to computation. And so a lot of the motivation for this comes from quantum computing, and in quantum mechanics, the quantum state can evolve in 2 ways, from unitary transformations or by their collapse. So this is where this gate comes in handy. And then, of course, it's universal. So, okay, this is a truth table here where they show these outputs. I was actually right on that, so that's good. There's this universality aspect where you actually, from one input bit, there are 2 possible reversible gates. One of them is not. The other is the identity gate, which maps its input to the output unchanged. So you can see that in quantum computing, we need to have more than the traditional set of outputs. And so this is just an example of a gate. And so there's another type of gate called a Fredkin gate, and also Deutsch gate. Deutsch from the Deutsch Church Turing thesis. Toffoli, who we will talk about in a minute, also developed a quantum logic gate. And this is another example of how you can represent a logic gate using symbols. You use Hadamard. Another type of gate is Hadamard gate. These are all quantum logic gates. So, maybe we need to have logic gates for biological computers. Actually, I think I've seen some literature on that where people have proposed gates for logic gates for biological computers. But that's something that, also for the brain. I mean, do we need to have specific logic gates for the brain as a computer? I don't know. So I talked about Fredkin gates, and Edward Fredkin was a physicist, computer scientist. He was interested in this area of digital physics, which is not necessarily the physics of information, but it's dealing with these digital systems. So he's a really interesting guy. If you've ever seen the movie War Games, he was the inspiration for Stephen Falcon, the guy who invented, I guess he was involved in the nuclear bomb or something. It's a fictional character who was based on Edward Fredkin. So Edward Fredkin worked on these type of logic gates. He worked on a lot of issues in computation. He founded some companies. He worked at MIT for a while, and he did a lot of work there. Also Carnegie Mellon. He had this vision of digital philosophy, which is really interesting because it's this sort of vision of pan-computationalism that is based in physical computation. So digital philosophy, he actually wrote some interesting papers on this, and it kind of gets like kind of outside the scope of physics, I guess. So the school of philosophy, which claims that all physical processes of nature are forms of computation or information processing at the most fundamental level of reality. Pan-computationalism is related to several larger schools of philosophy: atomism, determinism, mechanism, monism, naturalism, philosophical realism, reductionism, and scientific empiricism. So that's where that fits in the pantheon of philosophy. Pan-computationalists believe that biology reduces to chemistry, which reduces to physics, which reduces to the computation of information. So what they're saying is that if you think of the brain as a computer, what you can do is basically say that a biological system computes by reducing the biology of that system to a chemical system, and then reducing that chemistry to physics, and then reducing that to information, which is how physics is, computed. So this is definitely, if you're interested in this, check out some of the papers that he wrote on this, and even gets into the concept of the soul. He gets into this idea of all changes in physical nature are consequences of digital information processes. Nature is finite and digital. I think that's pretty controversial, but whatever. Everything in physics and physical reality must have a digital informational representation. So the stuff we've talked about with respect to digital twins, those digital twins are basically physical reality, which you could make a digital twin that includes everything about you, down to your sort of molecular physics. So this is an interesting set of ideas. There's more in digital physics from Wikipedia where they talk about this in more detail. There's this idea of it from bit. It gets into some things like the simulation hypothesis and things like that. So there's the Fredkin gate. Of course, we talked about that as a form of a logic gate. And then this paper, An Introduction to Digital Philosophy by Edward Fredkin. This is from the International Journal of Theoretical Physics, dated 2003. So this is all like, kind of gets into these ideas that he was developing. So I think this is interesting from the standpoint of a lot of the things we've talked about with, people talk about the brain as a computer. And sometimes they're talking about this stuff, but it's not immediately apparent that that's what they're talking about. So some of the ideas that are sort of implicit in what they're talking about are kind of laid out in this paper. It's a very interesting find. I didn't realize that. I didn't realize too much. I didn't know much about Edward Fredkin until this deep dive. So I want to go through some things very quickly. So there's this experimental demonstration of in-memory computing in a ferrofluidic system. So this is from one of the authors on this is Andrew Adamatsky. And Andrew Adamatsky has worked on, and we'll talk about this in a minute, mycelial networks and different fungi doing computing. So in this paper, they talk about in-memory computing as a ferrofluid system. So these are ferrofluid systems or magnetic fluids, which allow you to look at a number of different topics. They have this aspect of shape reconfigurability, where you can change them into different shapes. There is no evidence for their computing capability, but that's what they're going to explore in this paper. This water-based ferrofluid can perform electrical analog computing and be programmed using quasi-direct current signals and to be read at radio frequency mode. So basically you can do these analog computations, which are different from the digital computations that we're used to. And we can program these things using direct current signals. And we can read the output in a radio frequency mode. So you can manipulate it, you can stimulate these systems with a program, so you can stimulate them in a patterned way. You can put a program into it, and then you get an output. You can read it in radio frequency mode, what the output of that program is. So the logic gates are kind of a type of program, a very, very cursory program. A program would maybe be these logic gates in a series. So you'd have logic gates set up in a series of things, and then you have these, you have these outputs that tell you what the output of that program is. So it's like a computer in that sense. And so they actually have this, what they call memristive behavior. They have these memristive computers, which are actually physical computers that compute in a way fundamentally different from silicon circuits, featuring both short and long-term information storage capacity and plasticity. This is a colloid, so it's what they call a colloid in physics, is capable of classifying digits of an 8 by 8 pixel data set using a custom in-memory signal processing scheme, and through physical reservoir computing by training a readout layer. So they use different types of tools from computer computing and computer science to manipulate the system. So they're actually able to develop like a small computer from this system. And so this is actually not a living system per se. This is a ferrofluidic system. So these are these magnetic fluids that they can do these things with. They actually also do some work on mycelium networks. This is also Andrew Adamatsky and co-authors. And this is basically what they're doing is a similar type of thing with these mycelium networks. So the living mycelium networks are capable of efficient sensorial fusion over very large areas and distributed decision making. The information processed in these networks is implemented via propagation of electrical and chemical signals with on par with morphological changes in the mycelium structure. So this is kind of like a brain or like a network of neurons where you have this sort of plasticity, these morphological changes. You also have these chemical and electrical signals working. They're not organized in the way a brain is, but they're there. They're existing in a network. These information processing mechanisms are manifest in experimental laboratory findings that show that mycelium networks exhibit rich dynamics of neuron-like spiking behavior in a wide range of nonlinear electrical properties. So they actually do behave like neurons. They can get spikes, and spikes are kind of common in electrical networks for a number of reasons. There are chemical reactions going on. There's communication. So when you get this kind of spiking, it's, you can read it like a neuron spiking. So this is something that we can use to our advantage. An example of a single real colony, Aspergillus niger, we demonstrate that the nonlinear transformation of electrical signals and trains of extracellular voltage spikes. So you have these, you can transform these signals non-linearly. You can also train, you can get these trains of extracellular voltage spikes, so you can get a series of them where they have this encoded information like we talked about with the binary states here. There's information in these spikes. You have a spike or no spike. You have information. Then you can actually create a code where you compress the information in those spikes down to a smaller code. So that's something you can do to implement computation on a system like that. And this can be used to implement logic gates and circuits. The approaches adopted include numerical modeling of excitation propagation in the mycelium network, basically how those signals are then propagated throughout the network to different mycelia, and then representation of the mycelium network as a resistive and capacitive network, which are terms that involve electrical flow, and an experimental laboratory study on mining logical circuits in mycelium-bound composites. So they're doing a lot of stuff with physics and with biology in that group. They use this tool called reaction diffusion automata. I don't know if this will load in time. This is a long paper, but this is a book that is Andrew Adamansky's book on reaction diffusion automata, phenomenology, localizations, and computations. This is another book where he talks about these reaction diffusion automata. So these are computational devices, universal computational devices that we can use to look at some of these things. So cellular automata are regular uniform networks of locally connected finite state machines or cells. So each cell is a state, and then you have these transitions that the system can move between cells, and then they take this, or the cells can be modeled as a series of discrete states. And so cells take discrete states and update their states simultaneously in discrete time. Each cell chooses its next state depending on the states of its closest neighbors. And so this is how, and then these cells can be arrayed together and give us, some sort of computational answer, right? So I think that's it for that. I went through all the readings. Yeah. So let's look at the chat. Yeah, Fredkin died a few weeks ago. I know. I was like kind of surprised when I saw that. I was like, oh. Digital twin is a good regulator. Yeah, that's that would be ever good regulator theorem. Now there are some interesting connections there. We assume that we could build a digital twin that was identical to us, which is I think what digital physics would predict. There's this issue of the good regulator theorem and how that fits in. So we know from the good regulator theorem that maybe the number of states in the regulator and the regulated would have to match or be close, or at least be greater in the regulated or in the regulator than in the regulated. So I mean, we could, that's something I don't think they talk about in the book, but
yeah, that'd be an interesting thing to sort out. I don't have a lot more to say about it, but
yeah.
A lot of the readings just presented I feel like I don't know enough about or Andrew, but the Andrew Adamansky book, his work in general, the gates, even Feynman's lecture and stuff. I feel like there's a lot there. I really like. I don't know if these were quoting someone or just kind of said it offhand, but something about the heart of what computation does, transforming from one state to another. That line stuck out to me a bit.
Yeah. Well, I mean, that's just an observation. That's what your logic gates basically do, or even your codings, your information coding, is that you're basically transforming something into a more compact representation. So, a lot of computation involves representation. So you're representing something, right? It's like you have a series of ones, like maybe 10 ones, that could be represented as a single one. And you wouldn't lose any information because there's very little information in that sequence. It's just all ones. I can tell you what the next 1 or 10 numbers is going to be there. And you can just say it's a 1. You don't need to say it's 10 ones. It's like when you round a number, it's like all zeros. It's like, okay, 0. No, we don't care. That's the kind of thing that like is the transformation. Now, sometimes those transformations are lossy, which means that there's like, if you round pi, if you go to like the 10th digit of pi, everything after that is maybe like important, but it's not that important. We can cut that off, round it. We lose that information, but it's not that important. That's sort of a computation that we make, or maybe a computational representation of pi that we make. And so when we perform a like a operation like that, we basically create a representation for that. The output is a representation of the inputs in some way.
Yeah, and that's sort of like, it reminded of that quote from the Stanford Encyclopedia of Cognitive Science, which is like the main point of cognitive science is that there's mental representations and the computations that's done on them. It fits with that. Yeah, there's a lot. My mind's in many different places at once.
Yeah.
So.
Yeah, it would be useful to go back over this a couple times and get some information out of it. No pun intended. Amanda or Morgan, how are you? Do you have any questions?
That line about computation being like essentially the transformation of like one unit into another that also stood out to me, because that maybe that's a place where the difference between analog and digital really like arises. Like, what is the nature of that transformation? Maybe, I don't know, but yeah, that stood out to me. The fungi stuff is so interesting. That like really, I guess like any kind of like non-neural computation is really interesting because it makes us kind of question our assumptions about what neural computation is. Because we sit, like the assumption is kind of like, yeah, each neuron is like a gate, and then the relevant activity in the brain is going to be this abstract computational stuff. But if computation and cognition can happen in non-neural systems, then maybe it's not that level on which like computation is happening in the brain. That's also related to the immunology stuff that I was looking at. Varela has a paper that argues that like the immune system is a cognitive system. So I wonder if it would count as like a computational system. I don't know. It's all very thought-provoking.
Yeah.
We did some non-neuronal stuff before. I think that was mostly, well, I don't know if that was DevoWorm centered or not really. Maybe it was, but it'd be interesting to kind of talk about that. Maybe to continue this discussion series next time we can talk about. It'd be fun to do an in-depth dive either here or DevoWorm or wherever about like basically not neural computation or non-neuronal in general from the fungi to everything else, and also just sort of that very hashtag diverse intelligences.
Yeah.
And I'm kind of like, well, I'll say that later, but yes, that's interesting stuff for sure. I think that really lend to the methods, some of the methods project stuff too. Oh, I wanted to say before I forget, similarly to sort of the philosophy around that, everything we just said, I was thinking, I think my sense of intrigue about some quantum computing stuff has changed too, not just in light of this stuff, but also sort of like the philosophical implications for things like the different divides, like sort of those big supposed dichotomies, like digital and analog and discrete and continuous, and what does quantum lend anything or throw any wrenches into that, or does it just sort of shift those discussions any? I don't really know right now. Okay.
Yeah, I don't know. Well, I guess if you look at like a neural network or even like a brain, there are analog computations that get reduced to like digital outputs. So, like, I talked about logic gates. You can also have thresholds. So, like action potential is really like a bunch of things that are analog things. I guess you could call them analog things, where you get this summation of them, or you get this like threshold where they're active or non-active. So, like action potential is generated by a bunch of different types of ions being there at certain concentrations. That can be construed as or measured as a analog thing. The output then is measured as a digital thing, and you have some sort of rule that says this is what the output looks like. And so that's another kind of thing we have to think about, is that sometimes, especially in neurocomputation, there could be like these analog digital hybrid things that exist, and we're transforming from some sort of analog signal to a digital signal, and then we're converting it back to maybe an analog signal down the line. But that's all reliant on some substrate, some set of transformations, and so forth. Mm-hmm. So
there was another point that I'm remembering now very vaguely, and I don't know if it was a commentation on computation in general or specifically about physical computation, but it was something about, I don't really write it down very well, but it wasn't, I don't have a direct quote like the previous thing about state transformation. The thing about computation as like where the physical component of how the transformation is being done. And I can't articulate it very well right now. I'm trying to remember the words that you use so I can talk about them, but I can't find it, so I'm gonna have to come back to that.
Yeah, I think that this is pretty deep. So I mean, we have to probably go over this a couple times, and I'm not sure what we'll do next time on this deep dive. We might get into some of the stuff that we've done in DevoWorm on non-neuronal cognition or computation. I mean, there are a lot of things we can kind of follow up on here. We have a lot of threads. They're loose. If you have like requests, we can please put them in the Slack so I can address them, or follow up questions. I definitely would think about it a little bit and reflect, because it's just a lot of. I'll make this folder available in Slack. So between this lecture and the last lecture, there's a lot of stuff there. And the question is, how do we synthesize this a bit more? Yeah, also the notes document will have.
Yeah, I did capture, not completely, but I got a lot of the computational deep dive stuff in here. So
okay.
That can be added to and refined in the future. We have everything there. But yeah, please add to that if you want to.
Okay.
This is good.
All right. So the last thing, well, I guess we could do this. The last thing I wanted to talk about. Do we have anything else we want to talk about before I go into the?
Let me really quickly go through the rest of this.
Okay. Yeah. Why don't we do that?
Stuff, because this will be fast. We got this. I think we pretty much did this already. I'm going to close out hyperdigital designs. It was very well. But honestly, the hyperdigital designs, I know I talked about it before, but I might even put on my to-do list. Like, I should maybe write something about that for myself and for the lab, because I know that there's a lot of things from that continue to come up. So I might even I'm gonna make a note in Slack just to remind myself. that's off the board officially. Okay, I just lost everybody. Okay, here we go. All right. We're on standby for that. Should this be? Are we kind of on standby for the INCF thing, or is that done?
I think we're going to take a pass on that this year. We can put that in done.
Okay, great. Society for Neuroscience. I don't know if we're going to do anything with that at all. It's happening. We put it on here. It can probably all be closed out. I'll close them out later, but nothing else to add on this list. I don't think right now for like upcoming events, right? Okay.
I don't think we have anything major coming up. I haven't seen anything. The only thing maybe, we do have Neuromatch Academy on there, so that's good. I don't know. Let's try to maybe look for things too. I'm not sure what obviously we have the Neuromatch conference in the fall, but beyond that, I don't know what's going on these days with things. Usually they just kind of crop up as they come along, but I would definitely try to be a little bit, if people have events that they see, maybe bring them up in the Slack and we can put them in here. I know people do that already, but I want to make sure that we have a good lead time when things happen, so that we don't find out too late or have 2 days deadline to put something together. I think that's what happened kind of with the web conference on Mind Society or Philosophy of Mind. But that was, sometimes it's unavoidable, but to have a set of things maybe we can aim towards would be good.
Yeah. Can probably. This isn't really on standby. It's kind of an event for now. I'll go through this later. I think I might have put a call out. Hussein's adding a lot of stuff for opportunities, and Morgan posts a lot. But I think maybe just doing a general call for things that are happening towards the end of the year that we sometimes forget about. There's some of the Society for Neuroscience. There's some of the Triple AI also just put out its new call, the full one put out its call for stuff. I should maybe mention that in the Slack too.
I know we had those special topics that I think we missed out on, but I don't think that was something we could get together in time. So
yeah. I think previously I took those off. I took that off this list for later. There was some cool stuff in for embodiment too, but it didn't really. Sometimes it just doesn't hit. But yeah, I'll put another reminder in there and email stuff like that. I may even do I don't know, email blast or some other Slack update or something for that.
Yeah.
We talked about all this stuff. There were some things I wanted to talk about. Neuromatch, Google Summer Code stuff. Google Summer Code's going well. I really would like to get an AV or a video editing intern or science communication intern, but I have to plan that out more. My bookstore treasure hunting. Oh, I think this will show up. I found something very, very cheap, and I'm surprised at the hit rate because the turnover, these sort of. I know I'm being a little flamboyant about this, and I apologize for that. But it's funny to me, all the cool, these cool things that I'm finding, these old books that this one is $4, but just a Jean, well, it's not going to show very well. You can kind of see.
It's not really showing up. You have to, right. There we go. All right.
A Piaget book.
Yeah.
So it was super cheap, a few dollars, and the things that pop up in these bookstores around here, Cambridge, Boston area, are just kind of funny and interesting to me because they're actually it's really inspiring to me to have. I kind of went completely digital for the last few years, especially moving around and doing a bunch of stuff. But having this library of books, people that you can tell have been kind of efforting along the fronts we've been talking about and seeing the physical, having their books be these concrete things that you could touch and someone put thought into how this is organized. That's actually really inspiring to me at this point in my life.
Yeah.
So I'm kind of happy to like have this very small collection of people that have put effort into trying to sort out this mess that we're looking at all the time. I recommend it, especially if you can. If you're, I feel super lucky because it's like you can find this stuff on like Amazon, or when you find it for a few dollars, kind of like beat up used book
Yeah.
at a store. It's like, oh, like this is a total win for me because I'm not buying some used copy of the original, paying like a bunch, like $20 for shipping and stuff. So anyway, that's my continued book story, fun time thing. I think that's it for. I think that's it. So I think we're good. And any other? I know Morgan or Amanda want to say any more before we go into final stuff. I think that's it though.
One more note on the events. Like we do have a Slack channel for events, upcoming events. Maybe we can like go through that and make sure that that gets reviewed every once in a while and just put into the list.
Yeah, I did. Oh, there's a summer, a quote unquote summer school in August in the Netherlands that I just put in there. So in that aforementioned channel, which I also just mentioned
Yeah.
in Slack, but there isn't a whole lot in there right now. Just to check.
We have a lot of things. Some of them aren't really things that we would submit to, but they're just things of note. Our Slack, of course, we can't. We have like a 3-month limit on things, so the things will disappear, and so just to be aware of that. Yeah, I know. So yeah, that's great. Well, that's great. And like again, if we want to talk more about this, some of the things from the physical computation session, we can put them in Slack and revisit this next week. But right now, I want to finish up with a couple of things. Again, I was going to actually talk about, and I'll probably do this next week, about haptics. And so I have a session, or I have some readings on haptics and or like sort of the design of haptic interfaces and touch interfaces in VR and AR. So that's something we'll do next week. I don't think we'll have enough time for that. But I wanted to talk a little bit about spatial mapping and creating meshes. And to this, I'm going to go to some of the Magic Leap. So Magic Leap is a augmented reality headset that is it's a company that they've been developing these augmented reality headsets and creating ways to project digital objects into the real world. So if you put on one of these headsets, you can see like the world in front of you, but you see virtual objects pop up in your field of view. And so it's not magic to make this happen. Despite the name, you'll see objects that are tracked with your head, with your body, and you can select them. You can have things in the world. So it's really nice. But there's a technology behind this, and it's what I want to talk about. So this is a blog post on guided meshing in Create. So this is a Project Create that they have. This is guided meshing. So Create is a physics game that's played with and against your real world environment. So the idea when you first start up a Magic Leap headset, you do, and in fact this is I think true of MetaQuest and some of the other platforms, you create a spatial map. So basically you map out your space. In the MetaQuest, you usually use a guardian, which is a space around your body. You'll do some mapping to initialize the system. In Magic Leap, there's this process of spatial mapping of a space. So they use waypoints, and you walk around the space, and you kind of get a map of the space. The sensors on the headset make a map. So then that map is used for the applications to map the virtual objects in different places. So this Project Create is guided meshing. So this mesh is this creation of the space around you. It basically registers the space in the room, registers the space around the body. So these objects can be co-registered in that space. So Create is a physics game that's played with and against your real world environment. The excitement comes from building something magical in a familiar space. Having a rocket ship smash into your ceiling or a T-Rex chase a ball over your couch was the kind of new experience we wanted to explore. The quality of the spatial map or world mesh, terms we use interchangeably. So there's this world mesh, which is like this literal set of coordinates that radiates from your body out into the room or into the world that you're in. That's your spatial map, basically. And this is critical to the experience of this game. So one of the technical constraints we put on Create early on was no live meshing. So these meshes are nice to have. They can be created, but they can't be generated dynamically because the computational power isn't there. We don't have that ability to process, because this is a very computationally intense set of calculations. So it's not really easy to do live meshing, but you can build a mesh before you start your interactions in the room that you're in, and that's good enough. The user space would be scanned when the app started, and Create would then use that scanned mesh for the rest of the experience. Due to our AI pathing system, we needed a quality mesh before any virtual objects could be placed in the world. So they do use a lot of AI in these systems to do predictions, but you do need to have a good mesh to start so that things can be co-registered in that world. There are also design issues around resolving digital content that could be hidden when updating a spatial map. Finally, we wanted to use an initial scan to ensure the mesh at the beginning of the game met minimum quality requirements before we started. So this is, so we don't start with nothing. When an app requests a spatial map, it inherits the current world representation from the operating system. So the operating system has a mesh, and then you can do another mesh when you start the game. So you can have these, different representations of space. The more representations of space, or the more information you get about the space around you, the better, because it helps to sort of resolve things when you say turn your head or you start reaching out from your body. What's out there? Are there objects in the way? Or is there a wall there? Whatever. We tried different ways to tell users that they needed to look around the room, including text instructions and pointing to specific locations. So these are things like waypoints or other affordances in the space that you can use to enhance these spatial representations. In the end, we went for a more guided experience, so players could only start playing and Create once they had enough mesh. So this is a game that they're playing in space. They have this mesh. If the space is meshed, they don't really need a waypoint, but you can also create waypoints to have like points in space where you can use as reference points. So this is basically the user, the perspective of the user around them. They have this mesh in their room. This whole space is mapped out with a mesh, which is basically the set of coordinate points that the system can use to project images, to mediate when you reach out and you touch something, to know what the depth is, and so forth. And so this is the bounding box of so in your room you have a bounding box, and in MetaQuest it's basically that boundary. It's the same thing. It's around your body. It's this this area that within which you map out the space. So outside of that, the space is not mapped. And so there are different strategies they can use to map the space out. You can use the head-centered frame. You can use a hand-centered frame, and you have a walking path. And so there are different places where you can generate the mesh from, either from a head-centered reference frame or a hand-centered reference frame, which sometimes they call an end effector. Those are different reference frames, and having those two reference frames and being able to differentiate between the two is actually makes it more accurate. So you can interact with things more accurately when you have those readily available. And so they kind of go on about some of the more technical details: rectical, lock-on, and completion. They provide a digital content recticle. The recticle points to the incomplete waypoint nearest the user's forward HUD pose. When the player looks at that recticle, which is a point in space, we move into a lock-on state and display a timer. The timer runs as long as it stays within a minimum distance from the center of the player's view. If there isn't a mesh behind the waypoint, the timer runs at a slower rate. This optimizes the system's scanning time and helps us build a better spatial map for that location. So this is just kind of going through this meshing process, the technical details of how this is done. And so this is, this is a nice way to approach this sort of spatial mapping just through guided meshing. Now, Snapdragon is a hardware manufacturer for a lot of these headsets, and so they have this developer community of people. They have an SDK that you can develop on their hardware. They also develop hardware for cell phones, so they can do this sort of mobile AR, mobile VR stuff. Basically, they have a thing for their development community on spatial mapping and meshing. And so the way they view this is they provide users with an approximate 3D environmental model. This feature is critical in helping smart glasses and understand and reconstruct the geometry of the environment. So you can see that this set of glasses, they have a spatial map radiating out from the head-centered view. It has an angle, a viewpoint angle. So, you have this field of view that is maybe 120 degrees, maybe 110. And you have objects within that field of view that you map out. So when you reach out to the table, you know that there's a little vehicle here, a stack of papers underneath, this keyboard, this cup, this appointment book. You don't just reach out on the table. Things are, don't kind of overlap with those objects. And so that's the kind of thing you want to have in your representation. So they need to do this sort of meshing again. Spatial mapping and meshing offers both a detailed 3D representation of the environment surrounding the user and a simplified 2D plane representation. So they have two representations. They have this plane, which is a 2D plane, and then they have the 3D space. So they're using both of these to sort of calculate what's there and what the space looks like. Meshing is needed to calculate occlusion masks, which means when things are occluded by other things, or running physics interactions between virtual objects within the real world. And so they have this technique that they're using. They say, why do you need to use spatial AR? So they're trying to sell this to developers to get them to understand the need for this. So a big part of how well users perceive your application lies in understanding the environment and adapting your application to it. If you strive to achieve higher realism for your digital experiences, spatial mapping and meshing is the right choice. So you don't need to use it, but it's important to have realistic behaviors in your environment. So as humans, we can understand the depth of space using visual cues that are spread around us in the real world. Occlusion is one of the most apparent depth cues. It happens when entire objects hide from view, covered by other objects. So if I have a cup on my table and there's something behind the cup, I can't necessarily see that object. I have to move to see it, or I might be able to see cues like a shadow from that object, but I can't see that object directly. So you have these different cues, spatial depth, different angles of light coming and hitting it and providing these natural cues that we see in the real world. And so being able to replicate that is very important for interacting with objects. And so they've been working on this. This is what a mesh looks like of a space. You see it's kind of like a cover of the space. It's like you have all these points on this bunch of vertices on the surface, and they cover up things in the environment. So this space is being meshed. This mesh fits over all of these things, and it allows us to have a representation where like the shelves are, the computers, and you can refine this mesh more and more so that you can see behind this chair, for example, or behind these computers. See, this computer looks like a big screen here, whereas you have two distinct screens here. So if you refine this mesh, you can get the detail in between. And so this is what we want, and we want to get the most refined mesh possible to enable these interactions. So this is Magic Leap from their documentation. What is spatial mapping? This describes the way they do spatial mapping in more detail than what the first article did. They have these world features, which are 3D representations or point clouds, and they serve as the basic building blocks of a spatial map. So you can see these crosses being the point clouds, or parts of the point cloud where you have different points that are, sampled in that space. And then if there's an object there, it differentiates the depth from the background. You have these world models, which we talk about in AI and deep learning, but we also talk about in building these spatial representations. We have these dense meshes and planes that we use. So we use a plane for a surface and a mesh for like a space where we want to map differences in depth and other features like that. And then world understanding, which allows us to understand different objects in the environment and what class they belong to. So like this chair is a chair, we can identify it as a chair as opposed to just something in the environment that's there, a feature. So this is where AI comes into play, because we can use AI to sort of segment these spaces, these three-dimensional images, these 2D planes, and give semantic information about those spaces. So there's an interesting opportunity here to merge spatial mapping with some of the semantic segmentation stuff that we've worked on in DevoWorm, but also in AI, building world models and building like representations of different computational objects. Finally, then there's this other article from the Documentation on Spatial Mapping. It kind of talks about best practices and lighting and materials, distance of the range of the sensors. This is also from Magic Leap. And then movement, how if you move around the space, when you make these maps, you need to move around the space to make sure that the system has sampled everything properly and has a good representation. And so then there are some things that you need to be aware of when you build these maps, very practical things. It uses infrared sensors, so it's actually sensitive to different intensities of light, sunlight, or other kinds of infrared light that can interfere. You can have problems with like black objects, like black tabletops, or black things on the wall, or dark things on the wall. They can affect the absorption of the sensors and interfere with the map. And then you have weird angles, so you have to move around and approach things from different angles. You also need to have account for things like transparent objects and mirrors, which can also play with the sensors and their ability to build a representation. So I'll put all those in the Slack as well. I think that'll be useful for Shali, but also for other people interested in VR stuff. And that's all I have for that.
Yeah, like I said in a comment, I used a lot, and I used the LiDAR sensing on a specific app, at least on iPhone stuff.
Yeah.
And it's interesting how that's like more popular and what that can lend to. And like doing that with the mirrors was always tough. And you have a mirror in a doorway, a door that's open in a room, it can get really crazy really fast. And it's like you're trying to take measurements or do modeling and stuff with that. It's like, uh-oh. So that's always a tricky part. But I'm curious how I think there's there's so much that can happen with that. And I'm curious where the technology will create a lot of new potential quote unquote affordances that way. And I don't know. But it's an interesting discussion here, yeah.
Yeah, I think they're really kind of getting this, and I know Meta has a whole host of new technologies for their headsets, like they're coming out with a Quest 3 and things where they're able to build these rooms or these representations of rooms, and having multiple representations is actually a good thing because you can cross-reference them. So like if you have a room versus maybe like a series of environments. I know we have at home we have a robotic vacuum that actually maps rooms using LiDAR. Like it maps all the rooms in the house, and then you can just send it to a room, and it'll do it'll vacuum and mop the room pretty seamlessly. I mean, it doesn't have a lot of problem with it, but it continuously maps that space when it's going into the space. You can build a new map, but it actually learns from like some of the previous experiences. When it hits like a wall or hits an object, it backs up, and sometimes it gets caught, but like it's actually pretty good at like completing the entire room. So
Interesting.
Yeah. All right. Well, I think that's all for today. Any other comments or questions before we go, or anything you want to bring up?
If any, oh, I have a concluding thought or two, but I'll wait if anyone else wants to go first. Also, some people have a lot of, I don't know if it's like more Canadian forest fires, but some people are very bad air quality, so good luck with that. That's around you. I guess my concluding thoughts first are, go back to the mountains, are that clean mountain air.
Yeah.
I think some things to take away going forward that points were made earlier were, let us continue to review the deep dive of computation stuff is great, but also let's continue to think about our past papers. I think we have a lot. I think we have to go back to look at some of the non-neuronal stuff. You mentioned the Gibsonian paper, and even the interface focused paper. Looking at it again, like this passage is like, oh yeah, like there's so much stuff. Like you said, things were condensed to fit into that paper, but then it's like there could be more and more and more built upon that, and it really does fit. I'm very appreciative to be in the discussion. I'm in the paper, but I feel like I was kind of just along for the ride some there. But I really wanted to continue to build that forward, and so yes, yeah, let's continue to think about the past papers, and even in a sense of like as I'm doing some of these like Google Summer of Code, updating the website, updating this past stuff for our projects. I guess that's sort of I don't know. I guess I mentioned this before, like almost doing some kind of a recap, like a conceptual recap post. Maybe I'll try to draft that out for like the lab. Like we talked about these, the thing with the we're like the Macy's conference, and then I listed these sort of the common themes again. Maybe like a little bit of a where are we landmark, like just putting a notch on some trees and saying, hey, here's where we are right now. About this would be really good because there's stuff that's kind of the lines are I think easy for me to see and easiest for Bradley, but then they could be made a little more explicit to say, oh yeah, this is actually sort of the lineage of the discussion right now. So maybe that'll be something I can do. I'm motivated to have in my mind. I can start fleshing out now and just do a simple version of that. But I feel like there's a lot going on there. So between that lens and also the diverse intelligences lens, which is even seeing some language between like Levin's lab and his, I think I'm going to make it like a regular routine of mine to look at Levin's lab page and the articulate work he put into framing his research efforts. And it's very few labs do that. And I really appreciate that he's done. And it's also like, I understand why, given what he's doing, but also like it's inspirational to see that. So between that and like my old books and the language of diverse intelligences between the actual Disney conference and Levin's lab and everything we just said here, I think there's some stuff there. So to make it a little more concrete, yes to looking at the old papers, yes to fleshing out those old ideas. And I think that's something that we can really center as we go forward. The last similar concept of that would be I do want to do more like videos and segmenting to kind of get some of these chunks, like the computational deep dive today is a great thing. Like that should be a thing we point to specifically, but also like the oral discussion series concept. I want to do more with that. That's on my mind. If you have any thoughts about that or want to collaboratively brainstorm or bring any of those things out, please just get at me in Slack. But those are all kind of administrative directives I'm taking from this, and that's kind of what's going to be on my mind as I go forward. But that's all from me otherwise.
All right. Well, thank you for attending, and stay in touch in Slack, and talk to you next week.
Take care, everybody.
Talk to you soon.
Okay. Bye.
Thank you.